So this set S is characterized by being the set of all fractions, basically, where the numerator of my fraction is an integer, and the denominator of my fraction is a power of 2. Right? So it's a set of all rational numbers whose denominator is a power of 2, basically. And you're asked to decide whether that forms a group under addition, whether that forms a group under multiplication. Let me get a quick show of hands just going around the room. Who said that this yes forms a group under addition? If addition is the operation, does this form a group? We've got about half of you saying yes. How about multiplication? Yes or no? Maybe about a third of you are saying yes. Okay, so there's some conversation going on around this. So if your group had a chance to talk about this, what was the nature of the conversation? What were you talking about? Where are the points of disagreement here, for example? Maybe one of you want to make your case for why you think one of these is a group or not the other. Any key insights? So one thing that argues for this being a group under multiplication is that if I have two elements, let's call them x1 and x2, that belong to my set, then what do we need to deduce? What you were just saying? We need to deduce that their product, so product in the sense of actual multiplication this time, right, belongs to S, question mark, right? What's the name of that property? That's the closure property. So why is this true? Well, every element in this set can be written as some integer divided by some power of 2, so p1 over 2 to the k1, p2 over 2 to the k2. And when I multiply those together, what happens? I get p1, p2 in the numerator. Downstairs, I get 2 to the k1 times 2 to the k2. But how can I simplify 2 to the k1 times 2 to the k2? 2 to the k1 plus k2. Very good. Now, that's what x1 times x2 looks like. How do I know whether or not that's an element of S? Well, what do elements of S look like? Integers divided by powers of 2. P1 times P2, is that an integer?
Yes.
Sure, because the integers are closed under multiplication. If P1 and P2 are integers, then P1 times P2 is an integer. What about K1 plus K2? K1 and K2 were integers. What's K1 plus K2? An integer, because the integers are closed under addition as well. And so we have an integer power of 2 in the denominator, we have an integer in the numerator, therefore, closure. So that argues for this being a group. Right? But that's only one of our 4 properties. Did anyone find something else out about this set?
We found that the inverse property doesn't hold for multiplication.
Why does the inverse property not hold? So what's the inverse property say again? It's supposed to say for all x in S, there exists a y in S such that what is true? If the inverse property holds, how are these x and y's related? What does the inverse property say? Yes, but what makes y the inverse of S? X.
X times y equals e.
X times y is equal to the identity element, right? What is the identity? It does, first of all, is there even an identity property for this group? Or if there is, what is the identity element? 1. So 1 is the identity element in the rational numbers under multiplication, and 1 just happens to belong to this group, this set, rather. Because, for example, if you take p equals 2 and k equals 1, we get 2 over 2, which is 1, right? So we know for sure that 1 belongs to our group and actually satisfies the identity property. So anytime we talk about inverse, we really have to establish identity first, right? 1 belongs to S. Okay, so xy equals 1. So then why is this statement not true, Kelly?
So the inverse of p over 2 raised to the k would be 2 raised to the k over p.
Okay.
But this inverse would not hold true if p was any odd number.
Okay. So you're saying if you give me a element of this set, p over 2 to the k, I'm going to give you, for its inverse, in the case of rational numbers, its inverse is going to be just the reciprocal. Inverse for multiplication is the reciprocal, 2 to the k over p. But what you're saying is that this inverse might not belong to S. For example, when p is what kind of number?
Any odd number.
For an odd number would be an example of a way to make this not happen. And so if you're going to convince me that the inverse property does not hold, you should show me a counterexample. Show me a specific counterexample. This is another thing that for some reason novice authors of proofs are sometimes reluctant to do, is to get specific, probably because you've had your hand slapped on universal statements trying to be proved by explicit single cases in the past. But for a counterexample, how many counterexamples does it take to make a universal statement crumble? Just one. And you can be as specific as you want to be in that one counterexample. So give me an example of an element of S whose inverse does not belong to S.
If k equals 1 and p equals 3.
K equals 1, p equals 3. And so that would be 3 over 2 to the 1, right? So x equals 3 halves. This belongs to S. But its inverse, the only fraction in the rational number system which when multiplied by it gives me 1, is 2/3. But what's the problem with 2/3?
No.
Doesn't belong to S. Yeah.
My question is,
So what did we decide about this? Is S a group under multiplication? No. But to give away the ghost on part A, it does form a group under addition. So convince yourself of that fact. So the other problem that I'll talk about when I get back to my office is how do you rewrite an expression with a negative exponent using only positive exponents in a general group setting where we can't divide the way that we're used to in algebra. So this problem asks you to rewrite a couple of expressions without using negative exponents. And this is challenging for a couple of reasons. One of them is that the last time you probably saw a problem like this was in, Algebra 1 or Algebra 2, long time ago. And the usual trope that people use is that they see a negative exponent and they're just like, oh, well, that's 1 over the thing with a positive exponent, right? This is high school thinking. And the reason that it's high school thinking and it's not going to work for us is that we don't know what division means. And we don't know what 1 means, after all. I mean, we're talking about A and B being elements of some abstract group. And so there's only one operation in our group, namely the operation of the group, which sometimes we call multiplication, even when it's not actually multiplication of numbers. And we don't know what 1 means. But probably 1 is going to play the same kind of role in high school algebra as an identity element would play for the multiplication generic operation in the group we're talking about now. So we need to figure out a way of understanding what a to the power minus 2 is, whatever this thing is, that can help us get a positive exponent into the picture. So maybe I want to start by just writing this. A to the negative 2 is equal to a to the negative 2. So that's not controversial, I hope. But if I want to make this, expression, if I want to make this expression have no more negative exponents, I'm going to need to know something about a. And so you're given some information at the outset of this problem about the elements a and b. And this is essential information to actually making this problem happen. Because without this information, there is in fact no way for us to rewrite these expressions using only non-negative exponents. So the information we have is that a to the 5th power is equal to the identity. And so what I'm going to use that to do is I'm going to use the identity property to convince myself that, well, a to the minus 2 is the same as a to the minus 2 times e. But since e is equal to a to the power 5, that means that this expression is equal to a to the minus 2 times a to the 5. And now I have a product of 2 powers of a, and anytime I have a product of 2 powers of the same element, all the exponent properties that we learned in Algebra 1 in fact do apply. And what we get is a to the power negative 2 plus 5, which is a to the power 3. And 3 is indeed a non-negative integer. Right? And so a to the minus 2, it turns out, is just another name for a to the 3, when a's fifth power is equal to the identity. Right? So this information in the green circle is critical. We cannot do this problem without knowing that about a. And for exactly the same reason, because the seventh power of b is the identity, that means that the negative fourth power of b is also equal to b to the power 3. Just by multiplying this expression by b to the power 7, right, which is equal to the identity, and therefore it doesn't change the value of this expression. So maybe another way to think about what the work of doing a problem like this would look like is just to start with that whole expression, a to the minus 2, b to the minus 4, and maybe multiply it on the left side by a to the power 5, and multiply it on the right side by b to the power 7. We can do that, again, because both of those things are respectively equal to the identity. Right? And so we're not actually changing which element we're talking about, we're just changing the expression that we're using to represent it. And now when I combine this 5 and this negative 2 powers of a, I get a total of 3, and I combine this negative 4 and this 7 powers of b to get b to the 3. So that's the shape of what problems like this look like. And the only wrinkle in part B is that the power here is being taken not of a single element, but of a product of elements. And so, according to the hint over here, the way to charge ahead with this problem is to break apart the negative power into the negative part and the power part. So instead of a negative 2 power, think of it as negative 1 power and then square that result. And the reason that helps, if I take this negative 2 here and I make it negative 1 instead, and then I think about taking that whole thing and squaring it, that helps because this expression can be evaluated using the shoes and socks principle, right? Because it's the inverse of a product, its result is going to be the product of the inverses in the opposite order, b to the minus 4, a to the minus 2. So don't forget shoes and socks. Without shoes and socks, we're not going anywhere on this problem, because that's what allows us to eliminate the parentheses and apply that inverse to the things that are on the inside. Now all we have to do is square that result, which of course we have to be super careful to do. In particular, we cannot distribute that power because we don't know that, for example, that this is an abelian group. We don't know the operation is commutative. And this was actually the question number 3 in the multiple choice part of this daily work. We can't actually distribute that exponent unless we know that the group is abelian, which we don't. So the best we can do is write b to the minus 4, a to the minus 2, b to the minus 4, a to the minus 2. And now we'll use the same trick to turn these exponents from negative into positive, just by remembering that the fifth power of a is the identity. That means, just like up here, a to the minus 2 is equal to a to the 3. So we'll replace the a to the minus 2's with a to the 3's. And we'll replace the b to the minus 4's, likewise, by b to the 3's. And so if you really want to, I suppose you could write this as b to the 3rd, a to the 3rd, quantity squared, or something like that. But either way, the key observation here is that because we happen to know that there's some power of a and b that equal the identity, that's exactly what lets me rewrite negative exponents into positive exponents. That, combined with the shoes and socks principle, gets us to where we need to go on this problem.